Welcome to this lecture series on AC machines. Again, if you are a visiting viewer. Now, today we are going to talk about a couple of things that are important in AC machines that are kind of not connected together. So we'll go through a few related topics that I can't actually have a specific of put under one topic here. So first of all, we're going to start talking about reversing magnetic field direction. All right. In the previous discussion last time, we basically spoke about how we can set up a rotating magnetic field based on our ABC currents. This is assuming that we have a three-phase winding in our machine stator, and then with that three-phase winding, three-phase wound stator, we applied a set of balanced three-phase currents, and we showed that we have a net flux that is of this form. And then what this tells us is that total flux vector, the flux density vector, it has a certain amplitude and it rotates at the electrical frequency, the frequency that we apply the currents in. Okay, so it is rotating at that same frequency. Okay, now for a motor, it's practical to reverse direction. Okay, and how can we need to understand how that can be achieved. That can be achieved very simply by swapping any two phases. So for example, if you are to switch any two phases, you will see that your magnetic field now have a negative sign. Okay, so again, if you swap two more phases here, let's say we swap this one with this one, again the sign will change. It'll become a positive sign. All right, so this is the primary idea behind swapping or changing the direction of a motor if you want to go in the reverse direction. This also is important in setting up a machine for the first time, and you have to couple it into certain hardware. All right, because when a motor designer designs a motor, there is a certain polarity they call positive direction, and for that positive direction they will specify a certain phase sequence. So as you get a motor, or when you are looking at a motor, in order to determine what that positive direction is, that's something that you have to determine. Okay, especially if you are going to do field oriented control, and when you connect a position sensor to that motor, typically your position signal is a ramp. The ramp with respect to increasing rotor angle, and then the positive ramp tells us that it's it's in the positive direction. And if you don't have any data sheet, or if you don't have any information on that, you can choose what your positive slope is and what is the phase sequence that gets you to rotate in that selected positive direction. Okay, and it could be clockwise, that gets you this positive slope. It could be counterclockwise, that gives you the positive slope. So it's important how the windings and the currents relate to get you to that direction of interest. Okay, so positive direction or reverse direction, and that's achieved by changing the direction of the stator magnetic field, which is achieved by swapping the two phases. Okay, all right, so let's go into the next topic. This is also another useful topic, which is basically talking about mechanical speed versus electrical speed, or mechanical angle versus electrical angle. And we may come across these from time to time, and these are also important, and I want to highlight the primary difference between those two. Okay, now you're going to see motors of different pole count depending on the application. So the machines are designed to have certain properties, and as a part of the design process you're going to see a certain number of poles. With the number of poles you are going to see certain number of slots. So typically they will say, slot this many slots versus this many poles. So 12 4, 12 10, 12 8, so vice versa. You're going to see different number of poles. And I'm trying to highlight here the importance of those two types of poles. Okay, and I have two cross sections here. In the top one, we have two poles, and in the bottom, we have four poles. Okay, and if you are looking at in terms of pole pairs, here we have one pole pair, here we have two pole pairs. Okay, and then the physical relationship is, if we consider our flux density is highest along this direction, then if we go from this to the point where we see the next highest flux density, you're going to see 180 degrees electrical. 180 degrees electrical. That's how we define electrical angle. And it also happens to be, when you go from this peak flux density to the next return peak flux density, we are seeing 180 degrees of mechanical angle variation. Okay, so we need to note that for this one pole pair case or two poles case, you're going to see 180 degree mechanical angle and 180 degrees electrical angle. Okay, so the key point here is we look at the angle from north pole to near a south pole, and we measure the angle. Always that is 180 degrees electrical, regardless of the type of construction. But how many mechanical degrees does it span will change based on how many poles the machine has on the rotor, okay, or the stator, depending on the architecture. Now, when we look at this four-pole machine, you can see that the peak flux density of a north to the peak return flux density of a south, we have 90 degrees mechanical. However, we said that that's 180 degrees electrical, right? This is 180 degrees electric. So this is the relationship that you're going to see between different rotor architectures or rotor structures when you change number of poles. And we can simply capture that by this equation with the capital P being number of poles here. Okay, number of poles. Now this can be viewed from the back EMF perspective. For example, if you looked at the back EMF across a certain winding or from a phase to phase voltage when it's not connected to an inverter, and what you'll see that when you spin one mechanical cycle, if it's a single pole pair or two pole motor, you will see one full back EMF cycle for one 360 degrees mechanical rotation. However, if you look at the back EMF of a four-pole motor, you're going to see two back EMF cycles within one mechanical cycle. Okay, so two electrical cycles for one mechanical cycle. And that correlates with our equation here. And since we know the rate of change of angle is rate of change of angular velocity is the angular velocity, rate of change of angle is the angular velocity, we can show that omega E is basically PO2 times omega M. Okay, so depending on the frequency that you apply, now you can control the mechanical speed. So this is basically how we change the speed of a synchronous motor, because we can now control that mechanical speed based on our electrical speed. Okay, it does not depend on load. We can control that frequency and control the mechanical speed. All right, and let's go into a little bit more simplified version to try to understand what's going on here. And here what I'm showing is the cross section. This is the cross section, and physically it would look like this. You'd have, you know, two magnets mounted on the surface. There are other types of motors where you have interior magnets, but I'm showing you one example here just to get you an idea of how the machine would look like on the rotor side. Okay. Now going into looking at the mechanical speed versus electrical speed, or mechanical angle versus electrical angle, from a little bit of a different perspective. Now we talked about the different pole slot combination, right? And then depending on how many poles you have on the rotor, you do need to adapt your winding structure based on the number of poles, because you cannot rotate efficiently the same set of, you cannot efficiently use the same set of windings on a single pole motor and a 4-pole motor. So you're going to see a lot of torque ripple and cogging torque, and it's not going to be as efficient as a winding set that's optimized for each type of rotor pole count. Okay, so you do want to have to look at machine designs in depth to decide what's the best winding structure for that, or finding configuration. Now here I'm trying to use an inside out motor just to give all of you an idea of what is this, what's the relationship between electrical angle and mechanical angle. And I think this will capture the idea pretty clearly. So here we are looking at a north and a south, and then we have a set of windings in the center. Okay, and then we are looking at a cross section of this, obviously. So let's say we are just looking at something like that. So we are looking at a cross section just to see what's happening. To this winding, we are going to apply a sinusoidal voltage, which will result in a sinusoidal current. So with sinusoidal current, what will happen is, let's assume we have slip rings, so that we don't change we don't have to change polarity. We are not changing polarity, we are maintaining the same voltage. So these two terminals are going to see this is VAB, right? So this is AB. So VAB is maintained to this set of windings, and when that happens, you will see that in the positive cycle, these windings are going to rotate, and then in the negative cycle, since the current direction changed, it's going to go one full cycle, right? It's going to rotate and return to the horizontal state. Okay, so you're going to see one full rotation. Now, however, it's a little bit different when we have these 4 poles or 2 pole pairs, right? We have, how many? We have 1, 2, 3, 4 transitions that we can go through. So when we apply the same waveform, same voltage, let's say this is A, this is B, right? And then what will happen is, you are going to see that this will rotate from here to here, and then again in the second cycle. So for the first cycle up to here, like in this case, right, it rotated from here to here and then here to here. Okay, and in the second cycle it will rotate from here to here, then from here to here. Okay, so one, sorry, 1, 2, and the next one 3, 4. So for one full cycle, it only went halfway. It only went halfway. All right, and with two cycles, it will return to the original location. It will return to the original location. So that means what happened was, for the same electrical frequency, the motor speed actually was cut in half for the same electrical frequency. So just by changing the number of poles and rewinding with a new winding structure, we were able to change the motor speed without changing the electrical frequency. Okay, so this is a designer's decision that they can choose to do when they design a motor. Okay, so this is how you would see those windings, and again you're going to have slip rings at the ends, so that the polarity does not change, because we are talking about an AC motor here, not a DC motor. Okay, so hopefully this provides a little bit more clarification of how that changing of the number of poles will change or affect the mechanical speed if you maintain the same electrical speed. All right. Okay. So folks, if you have questions and if you need clarifications for people who are watching this, feel free to post comments or contact me, and I can try to clarify and update the videos, in the future. Now, another important topic is saliency in machines. Saliency, and that actually links to the inductance that a certain drive will see, a motor drive or an inverter will see as it rotates. And so before we begin this, I want to go into this basic circuit that we have seen before. This is a simple transformer with an air gap, and you have a coil wound around it. And when we studied it with Ampere's law, we took this closed loop around this transformer core or the inductor core, and then we came up with inductance as a function of reluctance. Okay, so what will happen is, if you change this air gap or the material, it will have an influence on the total inductance. Okay, so you can choose to fill this gap with material, and that inductance, that reluctance is different compared to having an air gap. Okay, so the same principle will apply to the machine. If, let's say, we have windings, we are only considering one set of winding, let's say A prime. Okay, in all cases, A prime A, A prime A, A prime A. Now this is the rotor, and the rotor is going to rotate, right? The rotor is going to rotate. Despite what orientation the rotor is at, A prime winding is always going to see the same amount of air gap. If you can imagine, my drawing skills are really good and I have the same air gap. Assume the same air gap length around the rotor. Okay, so that means it's going to see the same size, same air gap across around the motor. Okay, and in practice, this is very small air gap. I'm exaggerating here, and it's going to be consistent. So that means when we look at the reluctance and when we calculate the inductance, every time that air gap amount is going to be constant. All right. However, when we go into this motor structure, we can see that depending on where the rotor is, how the rotor is aligned, right? If the rotor is aligned this way, the magnetic path has a lot more air gap. If the rotor rotates and aligns in the horizontal direction, now we will see this air gap, which is much, much smaller. So that will have an influence on the total reluctance the windings will see. Therefore, the inductance will change. So this we call saliency. Saliency. And same goes for these type of motors. These are called interior permanent magnet motors. The magnets are embedded inside the rotor in specially made slots so that they don't move, or maybe a design consideration for reluctance torque. Okay, so again here, see, we have in this orientation we have one set of inductances, and then when you horizontally, when you move these to be parallel to this axis, you're going to see a different inductance because you don't come across the magnets anymore. All right, so depending on the rotor orientation, the AA prime winding will see a difference of inductance. So this is what we call saliency. Saliency, very important concept, and kind of trying to highlight how that effect, how the rotation will influence the inductance. In this case, it will see very small air gap. In this orientation, it sees much larger air gap, which will influence the inductance. Okay, and then this, when we look at further into synchronous machines, we will talk about LD, D-axis inductance, Q-axis inductance. So when they are different or when are they equal, we can discuss depending on different machine structures. All right. So I hope that was helpful. So please feel free to comment, subscribe, and let me know if you have other topics that you'd like me to talk about, or simply, if you want any clarification, feel free to reach out. Okay. So I'm going to stop the video. Thank you for watching.